So we are in the lecture 8, so week 8. And today we will be doing state space method. So week 8 had linearization of equation of motion. State space formulation. State variables. And solution of state equation. In that we had lecture number 20. Where we talked about introduction and what is the goal of control. Now, in this, we first learned that natural dynamics of a dynamical mechanical system is determined by the equation of motion. Next, we learned that natural dynamics can be changed by use of feedback control. goal of control is to obtain desired performance of a dynamical system. That too, in spite of changes in the internal parameters. Next is sensors are required to measure output required for feedback. Then feedback control with high controller gain. It achieve goal of control. So this essentially means that it is robust to internal parameter change and external disturbance. Feedback can stabilize an unstable system. Feedback can change the performance of the system. After that, we look at lecture 21, which was state space formulation. We learned that control is very vast field. And we will only looking at the primary linear and time invariant systems. And state space equation of motion can be linearized about an operating or equilibrium point. Next is relationship between state space formulation and transfer function. In lecture 22, we had solution of state equation. Where we learned about solution of state equation. In terms of matrix exponential. solution shows the trajectory of the system as function of time. This time evolution of the states. Now several methods are available. To obtain matrix exponential. For linear time invariant. SISO system. Then very useful concept for control system. Analysis. So before going into state space, let's take a short break. We will make my coffee, and then we will delve into whatever was left from the previous part, force and Newton methods. So how can we use that? Let's start the class. Recording is on. So we were continuing the last question, in which I had one elastic bar and the end was attached to a spring, and we try to find the differential equation of the bar, governing equation, as well as boundary condition. Now we got the natural boundary condition in the last class. Now next we have to find the weak form. So whatever we got is called strong form. And we have to find the weak form. Here the strong form is we are taking negative common. Everything is positive now. We know the domain that x is from 0 to L, and we have natural boundary condition as this is equal to so EA du by dx at x equal to L is equal to minus k of u coming from this spring, the additional spring. Also we have essential boundary condition that it is fixed at the starting end. Now what we do, we will assign u tilde as approximation of u such that the residue, so we know the residue is just so if we replace u by u tilde in the governing equation, we'll get residue which is not equal to 0. So u is approximation. Now weighted residual method. So it will end in where Bx is the weight function, test function, so it is from 0 to L. Now we'll put the values. So if you put the value, it will end in this equation. But here you can see in this term, we can use integration by parts. If you use integration by parts here, so there will be two terms. And there will be one more term. What we will do is that we will just write this like this, and now here we know that this v at we know that v at 0 will be 0 because v u at 0 is equal to 0, so it's known. So wherever u is known, we will become 0. So since u is specified at x equal to 0, hence v of 0 is equal to 0. So this is at x equal to L minus so, and the other one will be equal to 0. So this term will become 0 because v becomes 0 at 0. And finally we have this equation. In this equation, as you can see, we can use the fundamental lemma, and the weak form can be written, which will be 0 to L du by dx dv by dx plus so there is t by ea. So this thing here minus will be there. This into dx, and so this becomes our weak form. And what I'm doing is so this becomes our weak form. And what I'm doing is I'm extracting the
natural boundary condition so that we can have a matrix form. So let's put the values. So some values are given. So T value is 2 giganewton per meter. E value is 1 gigapascal. And area is also given. So we will put all the values and then we will see what happens. So T was 2 giganewton. 2 giganewton diameter. E was 1 gigapascal and area was 1 meter square. 1 meter square. Now K value was also given. K value is again 1 giganewton per meter. So everything will end as just root on 2. Where B will also be there. 0.2 B and this will cancel by itself. It will become 1 and L is also 1. So I am doing this problem because from here we can find everything numerically. So just for the practice question this is. Now what we'll do that we will this is the second part, weak form. So second part also done. This is the weak form. Now we have to describe the bar into 3 equal space elements. When using linear shape function, we have to calculate local stiffness matrix, load vector, global stiffness matrix, global load vector, and we have to solve for the unknown displacement. So next part is discretization. In discretization, what we will do that we will take the problem. So this was our problem and we will just take the beam. Since we know each and everything about the beam by the governing equations, we will just take the beam and in this beam there is a spring attached, so let us replace that also. Now we have to just take this green part, sorry, the grey part. Okay, so this was our beam. Now what we're doing, we're describing into 3 equal parts. Let's say this is element 1, element 2, element 3. Okay, these are points A, B, C, D. So this is the main. is divided into three parts. It's equal parts. So these are called finite element. And these points are called nodes. So now we will be defining some function. So we have got add function. Add function is nothing but, let's say at B point u value was this, and at C point u value was this. Okay. So how to mimic this value is by using add function. So what will assume that the function is like this. Similarly, at, let's say at A the value of u was this, and at D the value was this. So what I mean is, this is u1, u of A, u of B, u of C, and u of D. So these type of functions are linear interpolation function. And how can we define it? So let's define the point first. So this is x0, which is at 0. This is x1, x2, x3. Now we know that x0 is 0, and x3 is 1. So h, which is the element size, will be equal to 1 by 3. What I mean is, this is h, this is also h, and this is also h. And this colored function are defined as, let's say phi of x is such that it's x minus 1 by he hi from x I minus 1 to x I plus 1. Oh, sorry, ix. And so this will be one linear function. And this is second linear function. X I to xi plus 1. It will be 0 elsewhere. What is elsewhere? So below xi minus 1 and above xi plus 1. Okay. So as you can see, this, if we take at point C, at node C, we will see that the pink line, it goes something like this. So apart from the domain where the before x and the final when x add, it will have a add function. This is add, and apart from this domain, everything is 0. So this is our interpolation function. Linear interpolation function. Also, we can define as it becomes 1 for ith node and 0 at every other node. Now using linear approximation, in the weak form, we will get u, and there are 3 elements. So this is what linear approximation tells us. It is a summation of these add function. So similarly for weak function, so the wave function also, because as we have said it, in this Galerkin method, we are taking the u and v are same. So if we put it in the weak form, what is our weak form? We'll bring it from here. So this is global weak form, and what we have to do is we have to take it further, element y. And now we can modify this thing. So this we know, and here it will be u at x3 v of x3, because x3 is L or 1, right? So if we put the values, the above values, we will get now phi is only function of x, so ui are the constants which you have to find. Now don't worry about units, I have already taken care of them. So this into dx into space minus u3 v3. And if you would simplify it, like if we take out the summation outside, the g summation, since this is also having j and this is also having j, so we can take j summation common, and also vj is here and vj is again here, so vj also common, and whatever is left inside will be something like this. Okay, something like this. And hence we will get our elemental stiffness as well as force vector where psi a and psi j are nothing but element shape function. And theta is local coordinates. So this gives us our local stiffness and this gives us local force vector. But our question was to find for each element. So let's take our element number 1. And what I will do is just copy paste the figure from here element 1 have this thing, and we'll move other things. So phi a equal to 0, b is equal to theta by h, and k a 0 से h a dash by a dash d theta, which also again becomes 0. So this also becomes 0. KAB, which is equal to KBA. This is also equal to 0. What about KBB? The whole square d theta. So this will be equal to 1 by h, and this value is 300. This is for element number 1. Similarly for element number 2. Forces are also left. So F A is equal to 0 से h, equal to 0, but FB will be non-zero because this IB has value. So this will be h. So we get our local stiffness for element number 1. So we're going A to B. This comes at 0, 0, 0, 3. And force vector going from A to B is at 0, 1 by 3. This is for element number 1. Now for element number 2. So let me bring back the figure. So only element number 3. So we have to just look at the orange line. So it is between x0 to x2. So it is full populated matrix. So I just write all the values so that so this is we are talking locally. It will be equal to KCB. Similar case CC. And FB. So it was for 1, and now we'll talk about 2. Now we are getting the feeling that 3 will be same as 2, having one small exception. So when talking about UC, just change here only. KCC equal to 3, then CD equal to DC. So this DD equal to and here is the catch. So this thing will be this and minus U of 3. Okay. In the third element, only one change will be there. Here will be minus U of 3. Now let's construct so this completes our part A answer. Part 1 answer as local stiffness matrix and local vector of all the different elements. Now we'll look at the global stiffness matrix and global load vector. So in one line only we can write because this is our linear relationship. So K global, let me write in the set only. K global is equal to 0, 0, 0. So this will be 3 and 3, so 6. Minus 3, then 3 plus 3, 6. Minus 3, and it will be plus 3. So this is our K global, and U U global will be U0, U1, U2, U3. So in the above figure, we know U0, which is equal to 0. So this becomes 0, U1, U2, U3. And F global, it is equal to 0, 2 by 3, 2 by 3, 1 by 3 minus U3. So if you put these values into K global, U global is equal to F global, we can find out the value of U1, U2, U3 as well as U1, U2, U3. So there are 4 equations in 3 variables. So this won't be 0. Here some force will be there, F1. Where it is? So equation number 1, element number 1. So here one force F1 is there. F1 plus this. Okay, so this will be acting as F1 because that will be reaction force coming from the wall. So that I haven't taken. Other things are right. So F1, so here 4 quantities are there and 4 equation, linear equation, so it's solvable. So this answers our part second, global stiffness, and if we will solve, it will give us 3 also. So this was regarding the actual problem, and I want to come to beam today, but we are in shortened time, so I will just solve some practice assignment problem. So before knowing that, we should know about the eigenvalue problems as well as distribution to beam. So let me just write in the so I think everybody have done the basic vibration course in which there is one mass, one stiffness, as well as one damper. And we write this equation as, so this is x some forcing F. Alright, so this is called as basic vibration problem, and we know that static means this thing. Okay, and as you can see, this is also Ku is equal to F. So dynamics come if we take these terms. Alright. So which gives our problem as eigenvalue problem, and we know that natural frequency of this system is equal to under root k by m. Okay, so that means natural frequency is dependent on material stiffness and material density or mass. So how the material is structured. Okay. So natural frequency is very characteristic thing, and that is mathematically called as eigenvalues. So this is also called eigenvalues. So let's solve this question first. So they are saying that in dash, the eigenvalue is not the angular frequency of the system. So in spring mass system, we know that omega natural, which is one of the eigenvalue, is equal to 100 k by m. So this is the correct. Next is axial motion of the bar. Now axial motion of the bar means we know that a bar can be treated as spring. So if we have some bar, as in the previous question, and we are looking at this moment, so this can be treated as okay. So for that also, omega natural is equal to 100 k by m. This is also correct. Now beam vibration. So I couldn't go to the beam problem, but beam can also be treated as a spring mass system, just like axial bar. Just the order of the problem changes. Instead of second order equation, we get a fourth order equation. So beam problem can also be, so this was actually bar, now beam. In beam what happened, that the loading is in this direction, the transverse direction. Okay, so loading is in transverse direction. And hence the system can be treated as like this. It will have K equivalent. Okay, now this is also correct. So by logic, the fourth one is incorrect, but I will give a physical meaning of it. So buckling is something which is in between these two. Alright, so in between axial bar and beam, what happens that we are loading the beam in such a way that it buckles. Now we know that buckle is in axial direction, but the beam transverse loading is in transverse direction. So hence Buckling, first of all, is a non-linear. To give you the feeling of the buckling, what happens. So let's say a rod is like this, and these are the rollers. So such that this mean can roll like this, correct? But what if we restrict it in one direction? So we'll fix it into one direction, but now also it can do the axial thing. Okay, now what happens if this axial thing, so this force is applied that much, the alignment of this becomes something like this, so it buckles. Okay, it could have the transverse loading, like the loading can be in transverse direction, but then also it can buckle. So this is called as buckling. This is a non-linear equation, and since we know that this equation is linear, this is a linear equation. But the buckling is non-linear. And in non-linear equation, what happens? That natural frequency is not directly proportional to. So this relation doesn't help, and hence the eigenvalues are not the angular frequencies. Okay. So the question is the primary variable for the island Bernoulli beam problem are displacement and slope. So there are two senses of fourth order equation. So it needs four boundary conditions, and out of the boundary condition, essential boundary condition requires displacement as well as slope. Next is writing the Lagrangian approximation function can be used in Timoshenko beam, but not in the Euler-Bernoulli beam. Why? So first option is Euler-Bernoulli beam has 2 degrees of freedom, while Timoshenko beam has 1 degree of freedom per node. So this is wrong. It is also having 2 degrees of freedom. Now Euler-Bernoulli beam has 1 degree of freedom. So Euler-Bernoulli beam also has 2 degrees of freedom. So both these are incorrect. Now both beams have 2 degrees of freedom. Yes, the 2 degrees of freedom for Euler-Bernoulli beam are represented by the function which are dependent on each other. So here is the problem: independent. Okay. Now primary variable for Timoshenko beam can be expressed as, and which of the following statement is not true regarding the shear locking. Now we knew that what shear locking means. It happens in the finite element method of Timoshenko beam. Here what happens is we take approximation of the slope as well as for the displacement, and they have coupling in between. So if we take one linear approximation of the slope, we get linear the quadratic approximation of the um, displacement, and then um, the bending energy becomes zero because of the approximation we are taking. So this is not a numerical issue relating to the rounding of error, but something related to the approximation we are taking. Okay, so this thing happens, and shear stress becomes constant. Shear stress becomes constant, as well as it depends on what degree of polynomial we are talking about. So if m is equal to n is equal to 2, then it becomes shear locking. If it is greater, then we are above the shear locking. The next question is, which of the following statement is true about an eigenvalue problem? So eigenvalue are characteristics of the mathematical mode of the problem, and eigenvalues changes due to the change externally applied load. So as we have seen in the previous equation, that mu dot or double dot plus ku is equal to L. So the eigenvalue is equal to under root k by m. So there is no function of so we know natural frequency is equal to root k by m. There is no term of f anywhere. Okay. So eigenvalues are unique to a particular system. Eigenvalues are characteristics of the mathematical mode of the problem, but eigenvalue changes due to change in external load applied. This is incorrect. We have to write false. So B is our answer here. Next, which of the following statement not true about Timoshenko beam? Primary variable displacement slope. This is true. Let me write true. The secondary variables are shear force and bending moment. This is also true, just like earlier beam Bernoulli equation. Now cross section which are normal to the plane to the longitudinal axis remain normal. So this is for Euler Bernoulli, not for Timoshenko. In Timoshenko, the cross section which are normal to the plane to the longitudinal axis doesn't remain normal, but it goes at angle, and we have to provide the shear correction factor. So for a Timoshenko beam, the stiffness matrix for linear 1D element is it's 4 into 4, just as Euler Bernoulli beam, just having lot of term inside it, but the size is 4 into 4 only. Which of the following options do not influence the eigenvalues of the system? So external forces. Now boundary condition, I will give you an example that we were talking about buckling once. So if we take this buckling example, and we say that before moving in this direction, we pin this from where it is going. So from point where the buckling starts, we pin the system. for we provide a boundary condition, additional boundary condition. So what happens that it won't buckle now. Okay, now it will have a second mode of buckling, such as it will buckle something like this. Okay. So if we change the boundary condition, we can change the natural boundary, the natural frequency, but it doesn't depend on the external forces. Okay. So there are more questions which I've already solved here. It is for axial beam, axial bar only. Very simple problem. So you can go through these all of these problems for practice. And time is up. Hi guys. So I took class at 3 p.m. to 4 p.m. but time and class, but went very well. In which I solved two questions, and there was we solved one question, but here I will solve two questions, and there were some questions asked before the class, and some of them I am mentioning them again. So our first question was, there are a lot of alphabets and symbols in the course. So is there any outline? Is there any outline to the structure of the course? And I am getting a little bit confused. So so his doubt was generally like why we are doing this, and what is the general format of applying finite element method and some sort. So uh, so I just told him that the aim is to find the solution of a physical model, and before that we have to do something called abstraction, which is nothing but converting the physical model into a mathematical model. This mathematical model have some assumptions into it. So it's kind of any reality is converted into first mathematical form, and then we try to capture the physics of the problem, or we wanted to find some relevant quantities in the problem. So we try to approximate everything, because the problem is we cannot find the exact solution of each and every problem. So hence we kind of sought to we come to this finite element method, and here is the rule of finite element method. So this model has an approximate solution. So this has an approximate solution, and that is find out using finite element method. For example, let's say we have some eraser, because actually everyone had this example. They have observed the example when we can do the bending, and we can also do little bit axial. But whatever we have studied in this course, um, it is just idealized form of it. For example, if we take as a bending, so in that to pure bending, so it is something like this. So Euler-Bernoulli beam principle tells that this cross section remain parallel to each other or normal to the plane of bending. So hence this is always perpendicular, but this is not a real solution, because actually it is something like this, and which is covered in Timoshenko beam. So let me just, so this is Euler-Bernoulli, and this is Timoshenko. Okay. So which is more real? Timoshenko is more real. Euler-Bernoulli is more ideal form. So our main aim is to convert the physical model into some problem in this course, that is SKU is equal to F, where U are generally shown by displacement vector, and force is generally this is a force vector, and this is our stiffness matrix. Okay, so this is the symbol which we have used throughout the course, and in Jane Reddy book this is there. So the stiffness K is a matrix, and it depends on how much nodes you have taken, as well as yeah, so here the discretization come into the picture, how we are describing the system. So we are converting the large body into some smaller pieces, and now we are formulating for this smaller piece, that is called a weak form of one element, and then we are providing so we are assembling it, and then finally we get a global matrix, and we try to solve it and find the value of missing U and F. So this is the general procedure by which we start with a physical model, and then so we start with, in this course we start with a mathematical model actually, and so abstraction is not covered in this course. So that physical mathematical model, we try to find the approximate solution out of it, and finally we get a finite we use finite element method to find approximate solution. Okay, so this was the first question. Then second question was, is there any method by which we can get natural boundary conditions of the system? So yes, there is one more method by which, there are actually many methods, but one method which you have studied from 9th, 10th, 11th, 12th class. It's called Newton's law. Newton law is nothing but drawing of FBDs, free body diagram, where we take a part of the free body and then we try to uh, put the force direction. For example, if this block of mass m is moving in this direction as x, then it will have some d-Lambert force as this. So this we can find out using Newton law also. So this is just like a natural boundary condition or force condition. But why we are not using in academic or in scientific way? Because Newtonian law has a lot of problem, because for each particle we have to look at the direction of the forces and we have to equate them. So it takes a hell lot of time if it's not generalized. So hence for generalization we use something called Hamilton law. Or language equation of motion. So what that do, that it generalize the system such that finally we get a governing equation as well as boundary condition, natural boundary conditions. And what does this method require? This method require only the energies in the system and also essential boundary conditions. So if we have these two things, so we can apply Hamilton law and language equation of motion or language equation of motion, and we can get governing equation, natural boundary condition. Now in our case, where we are using Hamilton law in, let's say, 1 degree of freedom, which is given in the above figure, we can write this governing equation as ms dot is nothing but a so there will be some force which will be like this, so plus uh, equal to 0. Okay, so force plus mx double dot is equal to 0. So this is our governing equation. In natural boundary condition, we can see this as there will be normal and here will be mg. So this is also a governing equation, but this can also be natural boundary condition. But for large particle or for continuum, the Newton law loses its power, because we have to be keen in the directions. There are generalized method for Newton laws, but Hamilton law, the requirement is simple. We need a scalar energy, and we can find out how the configuration is. So the final result is getting out the governing equation, natural boundary condition. Now, Hamilton law and Lagrange equation of motion have its root called calculus of variation. So it's so wherever you have term use first variation is equal to 0. Is it nothing just like finding the maxima and minima of a
So in when we are finding the maxima and minima in our 8th or 10th class, we saw that we used to find the derivative of the quantity, and we were putting the derivative is equal to 0. Then we were finding the double derivative, and we were to finding if it's greater than 0 or less than 0, which will give us that it is maxima or minima. Similar approach is calculus of variation, where instead of a function, a functional is there, and we find out the first variation of it if we put it as 0, and that gives us our Hamilton law, and we can convert the Hamilton law into language equation of motion, because that we can do in by using Euler language formulation. So let me answer the related question. Fourth question: what is delta operator? So delta operator is called variation. To explain visually, so let's say this is a 3D diagram, and this is y, this is x, and this is z, and there is some surface. Let us take this as y. Let us take this as y, and this is z, such that z is a function of x and y. Okay, let me show it more visually good. Okay, my mouse is not working properly, but I will first. Okay, so let's say this is a surface on a 3D surface, and the z is a function of x and y. Now, if somebody say what is dz, so dz will be some small area dx and dz, or dx and dy. If we take that, so dz can be defined as that. Okay, so what is mean by this? This dark green thing. Okay, but what del z means? Del z means this, like having a different surface altogether, such that having this together, such that the ends are same, but it is having a different surface. Okay, so ends are same, but it is kind of, let's say, having this surface. So having a different topology is what I mean. So having a different topology. Okay. So this thing is called del of z. So d of z is this, and del of z is this. So it's a variation of a functional as compared to a small z. It is variation of z. In English language, it means nearly same, but mathematically, it has a huge difference. Now, how does ANSYS and Abacus software work? So, the general format is they convert the mathematical model into matrices, and they solve that matrices and find out the solution, and then pre-process the data and gives us other solution, like whatever is required from the model. So the first step is discretization, and so that is called meshing. So let me write down. So we provide mathematical model, then we mesh it. Mesh is nothing but uh, discretization. Then we provide governing equation. Now this governing equation can vary. So how much accurate we are taking depends on how complex it is. So for example, we have learned Euler-Bernoulli as well as Timoshenko. And we saw that governing equation for Euler-Bernoulli and Timoshenko are different. Timoshenko being more nastier one, and Euler-Bernoulli is much simpler than Timoshenko. But so it's like idealization. So this is more over the more ideal, and this is more real. Okay, so the graph goes like this. They are much more geometrically correct beam model, which you will eventually study if you are into the research. So, and we provide governing equation, and we define for one element, and then we try to find k matrix, and then from k we solve the system and we find u and f. Okay, and then we pre-process the data to find all the thing which is required. We will solve one example today related to that. Now, what is equivalent stiffness? So to answer this, first of all, the body should be flexible to have a stiffness, the value of k. Actually, what does k equivalent mean? That is the question. So in the eraser, so instead of a spring, if you put a eraser there, such that it is compressed like this. So if we have a spring and we compress, sorry, I have a spring actually. So if we have a spring and we give some force like this, okay, some compressive force, some force like this. So what will be K equivalent? So K equivalent will be nothing but EA by L, and this we saw in our one of the example. Similarly, torsion has GJ by L, so similar kind of quantities, and bending also have similar kind of quantity. So my point being that K equivalent can be found by using what type of physics you wanted to capture. So if you are taking the same eraser, and now we are saying that we are bending it such that it we are
giving it this kind of a force, okay, so that it should get perfect circular shape. And now we wanted to find stiffness. So we wanted to find the equivalent stiffness. So as you can see, this won't be equal to EA by L. It will be equal to something else, which will be bending stiffness, not the axial stiffness. Okay. Similarly, go for torsion stiffness. So hence, equivalent stiffness means like which physics we are capturing, and it varies from various situations. Now we will solve a question. So these were the questions which I kind of repeated. It was asked in the class, and okay, I will start the question now. Just a second. Okay, so we already know that K equivalent axial K equivalent of an element. Now first we will define what an element is. So element is this. Okay, and so what its value is EA by HE. HE being the length of the element. So this is our K equivalent. Here finding stiffness for element 1. So EA by HE, which comes out to be, so the values are given. E is 72 GPa. Similarly, stiffness for element 2, we can find out. This is for 1. So which is same as stiffness 1. We'll find stiffness for element 3. So which gives us all the stiffness for the all the element. Now we have to assemble the stiffness into global stiffness. So these are the local stiffness. Let me write local stiffness for element 1, local stiffness for element 2, and local stiffness for element 3. Now we'll find global stiffness. So we're taking it common. 1 minus 1 minus 1 1. Now 1 plus 1 minus 1 minus 1 1. 1 plus 1 minus 1 minus 1 1. And others are 0 0 0 0 0 0. So this is our K matrix. Now we will define our U matrix, U vector and F vector. So this is 2. This is also 2. So let me write F. It is nothing F1, F2, F3 and F4. So these are those points 1, 2, 3 and 4. We know the forces at 2 points. And 2 points we don't know. So F1 we don't know. F2 is given, which is P1, and F3 is P2, but in different direction, and F4 we don't know. Okay, so this is our force vector. We will just transfer it here. Now, so we will value is minus 200 kilonewton. So we have net, and hence it is solvable. So let us write all the equations. So it may take some time.